We are all surrounded by sounds, all kind of sounds. No matter where you go, your ears are able to catch some kind of sound. Sounds help us enjoy and identify things around us, whether it is the sound of birds chirping or people typing on a keyboard. Our brain processes a lot of information just by sound. But there's so much more to sound than our own sense of hearing. And in this video, we are going to see about sound. Welcome to the channel Get Smart. First, let us see what is a wave. A wave is a disturbance accompanied by a transfer of energy. Waves are produced as a result of vibrations and can be classified as transverse or longitudinal. In this video, we are going to see about the sound waves. Sound wave is a good example for longitudinal wave. So now let's look at longitudinal wave. In a longitudinal wave, the particle displacement is parallel to the direction of wave propagation. The particles do not move with the wave. They oscillate back and forth about their mean position. When traveling through a medium, these waves create compression and rarefaction. Compressions are high pressure regions where particles are close together. Rarefactions are low pressure regions where particles are spread further apart. One simple example to generate a longitudinal wave is to push and pull the slinky horizontally. Material medium is necessary for the transmission of sound from one place to another. So sound cannot travel through space since there are no molecules to travel through. But here on Earth we have air molecules to vibrate around our ears. The bell jar experiment proves that the sound requires a medium to propagate. Here the electric bell is suspended inside the airtight bell jar. After pressing the switch for the bell, you will be able to hear the bell clearly. The bell jar is connected to a vacuum pump as shown. After pumping the air out of the jar gradually, you will hear the sound becoming fainter, although the same current is passing to the electric bell. So when less air is left inside the bell jar, less the sound becomes. If the air is removed completely, you won't be able to hear any sound. So from this experiment, you can understand that sound cannot travel through vacuum. Now the question arises, can sound travel through other medium as well? To understand this better, do a small activity. Lay your head on your study table such that your ear touches the table. And now scratch the table gently with your nails. You will surely hear a distinct sound. And that's because the sound travels from the table to your ears. And you must know the sound travels faster in solids than in liquids and slowest in gases. This is because solids have much higher elasticity as compared to liquids and gases. Elasticity is the ability of a deformed material to return to its original shape and size when the forces causing the deformation are removed. So now, solids have much higher elasticity as compared to liquids and gases. Now if you see the solid substance at the molecular level, atoms are closely packed, allowing sound waves to travel quickly through it. Now you would have got an idea about sound waves. Now let us see about audible and inaudible sounds. The average human ear has an audio range between 20 Hz and 20 kHz. What this means is that human can hear sounds only that have frequencies between 20 Hz and 20 kHz. This is called audible sound. And those sounds which human ear cannot hear are called inaudible sounds. And the sound whose frequency is less than 20 Hz is known as infrasound, and sound whose frequency is greater than 20 kHz is called ultrasound. And this range differs to person to person. For example, young children, they can hear up to 30,000 Hz. And as you get older, as age increases, the range reduces. And it's not just dependent on age. The range varies from person to person. Also, animals have different audible ranges. If you take whales and elephants for example, they can make sounds whose frequencies are lesser than 20 Hz. And if you take examples like dolphins and bats, they create sounds whose frequencies are much higher than 20,000 Hz. Infrasonic waves are utilized for monitoring earthquakes, charting rock and petroleum formations below the earth. And also it is used to study the mechanics of the heart. And ultrasound is used to detect cracks in metal blocks, in electrocardiography, finding distance using sonar, and so on. All objects in the universe have a natural frequency or set of frequencies at which they vibrate. If the natural frequency of the body matches with the frequency of externally applied periodic force, the body readily begins to vibrate with an increased amplitude. And this phenomenon is called resonance, and the corresponding vibrations are known as resonance vibrations. Do you know? Soldiers are not allowed to march on a bridge. This is to avoid resonant vibration of the bridge. While crossing a bridge, if the period of stepping on the ground by marching soldiers equals the natural frequency of the bridge, it may result in resonance vibrations. This may be so large that the bridge may collapse. The ability to recognize sounds and identify their location is because of auditory system. The auditory system is the sensory system for the sense of hearing. It is comprised of two main parts, the ear and the brain. The ear's task is to convert sound energy into neural signals, and the brain's task is to receive and process the information those signals contain. Now let us see the journey of sound to the brain. We know that the source of a sound creates vibrations that travel as waves through particles in air, liquids, or solids. The outer ear catches the waves, which then travel through a narrow passageway called the ear canal. The sound waves hits the eardrum and makes it vibrate like the head of a drum. The vibrating eardrum jerks a bone called the hammer, which hits the anvil and moves the third bone called the stapes. These bones amplify or increase the sound vibrations and send them to the cochlea. The cochlea is filled with fluid, and the sound vibrations create the fluid ripple, which creates waves. Hair-like structures called stereocilia sit on top of hair cells and are grouped together as hair cell bundles inside the cochlea. The hair cells inside the cochlea ride these waves, and the hair bundles are moved. This movement triggers an electrical signal that travels through the hair cell into the auditory nerve. Different hair cells respond to different frequencies of sound. The hair cells at the base of the cochlea detect high-frequency sounds. The hair cells towards the top of the spiral detect low-frequency sounds. At the very top of the spiral, the hair cells detect the lowest frequency sounds. The auditory nerve carries the electrical signal to the brain, which interprets the messages as sounds that we recognize and understand. Not everyone has normal hearing. Exposure to loud noises and some drugs can kill hair cells, preventing signals from traveling from the ear to the brain. Diseases like osteosclerosis freeze the tiny bones in the ear, so they no longer vibrate. And with tinnitus, the brain does strange things to make us think there is a sound when there isn't one. But when it does work, our hearing is an incredible, elegant system. Our ears enclose a fine-tuned piece of biological machinery that converts the cacophony of vibrations in the air around us into precisely tuned electrical impulses that distinguish claps, taps, sighs, and flies. So in this video, we saw what is a wave, types of waves, audible and inaudible sounds, resonance, and the science of hearing. So when I speak about waves, there is one effect which comes to most of your minds. Yes, the Doppler effect. The link for the video of Doppler effect is given below in the description. Check on that. Thanks for watching.